Hello, Mr. Colati here, and today we are going to continue our study of logarithms. In our last lesson, we learned a little bit about what logarithms are. Today we're going to look at the last function in our function family, the logarithmic function. So, remember f to the negative 1? Actually, we have a special name for this. This is called the inverse of a function. This is the function that undoes an original function. How do you find the inverse? Do you remember? You have to exchange the x's and y's. So if this is y equals 2 to the x, to find the inverse of this function, you have to exchange the y's and the x's. And then you have to solve for y. Now, how do you solve for y here? How do I take apart an exponential like this? Well, you have to use the definition of a logarithm from our last lesson. So, if you remember, this I can rewrite as log. Okay, the base is always the same, so this is 2. Instead of the y being here, I put the x here. So there's my inverse. So we understand that the logarithmic function is just the inverse of the exponential function. And this has a lot of practical use for us. So first of all, let's write this out. Y equals log base A x is the inverse of y equals a to the x. The first practical point of this is that it helps me draw the graph. If you remember what an exponential graph looks like, or exponential function, it has an asymptote here, y equals 0, and there's a small following the asymptote in the negative, and then it shoots up very, very quickly. This point here is, if you remember, 0, 1. That is the exponential growth function. If I know that the logarithmic function is the inverse of this function, then I know that the logarithmic function is going to be a reflection of this function along the line y equals x. Let me get my, let me draw that mirror line for us. So there's my mirror line y equals x. So now, and I'll draw this one in red. So instead of this point being 0, 1, remember we can switch the x's and y's, so this is going to be 1, 0, so it's going to go right here. And then instead of going toward the negative x, we're going to be going toward the negative y. And then we're going to be shooting up like that. So that is the logarithmic function. I still, even to this day, I find it useful to draw a log function to think of it as a reflection of an exponential. That's the easiest way to draw this function. Before we go any further, what is a logarithm? What really is this function showing me? There's a few places that you'll see it in science and math. One is the Richter scale. So if you remember, there's, you can report an earthquake as a 7.2. But the Richter scale is a logarithmic scale. The decibel scale, which measures noise intensity, is similar. Really, for me, I think what helps explain logarithms is that, like I said before, we discovered, and that's in quotation, logarithms before we kind of figured out exponents. Because logarithms allowed us to, we use them to change the scales of graphs with very large data. So here's an example. And this is ripped from the headlines of the coronavirus, but a long time ago, right at the beginning of the coronavirus, when we were still figuring things out. So here you have Italy, that's where kind of the first big Western outbreak happened, and then you have the US data here. And this is just a linear, these are regular scales, so these are days and this is number of cases. And you can see, we know the coronavirus grew exponentially. Then the graph is kind of useless, right? I have no idea what's happening in this region here. It's very small numbers. Because everything grows so quickly in an exponential, really only the last few points, they really affect the scale of my graph. So I look at these two. It's hard for me to tell which is worse, Italy or the US. It's also hard for me to tell what's happening here. Now look at the second graph. This is the same data with the logarithmic scale. So the days on the x-axis are still go up by 1 each time. But now, if you look on the y-axis, every major tick mark here goes up by an order of magnitude, goes up by 10. So this is a log scale. I've taken these numbers and I've logged them base 10. What's the logarithm of 100 base 10? It's 2. What's the logarithm of 10,000 base 10? It's 5. So these numbers are each one goes up by a different amount, but once I've logged it, now the data looks different, and the data gives me a lot more information. We can see that the US data is increasing, right? This graph is increasing, whereas the Italy data, the number of cases is starting to taper out. So logarithmic scales are used in the Richter scale for earthquakes, for decibels, and you can use them in other scientific and population data experiments. You can see it's a different way to present your data. So that's kind of my explanation of logarithms. Okay, let's do what we do with all of our functions in the function family. Let's look at transformations. So this plus 4 is inside the bracket, we would say. So that means it's a horizontal translation. It would be 4 to the right, but because it is horizontal, it's reversed, so it's left 4 units. So now that graph that I drew up here, I'm going to take that thing and I'm going to move it. Oh, you know what I forgot to draw on it? Oh boy. Oh boy. Forgot to draw the asymptote here. So this is x equals 0 as my asymptote. So now that asymptote has moved over 4 units. So it's going to be somewhere over here. So it's going to be x is equal to -4. And the function, instead of going through this point, oh, I forgot the label as well, 1, 0, that's going to go 4 to the left. So it's now going to go through the point -3, 0. Now I draw this, and like that, something like that. There's really only so many key points to worry about here. The asymptote, the point, and then that shape. Okay, what about in here? I have a 2 inside the bracket. So this is a horizontal stretch. Oh, it would be a stretch, but because it's reversed horizontally, this is actually a compression by half. So I'm going to take the asymptote's not going to change, but this point is going to be compressed. It's going to be squeezed inward. So it's going to now be at half 0. So I get this shape. Okay, last one, negative. So negative, I know this is a reflection. The question is it a reflection in up, down, or side to side? Well, if it's inside the bracket, it's horizontal. If it's outside the bracket, it's up, down. So this is a reflection in the x-axis. So this point actually will stay the same, but now it will come like this. Oops. And there's my sketch. The asymptote stays the same as well. So transformations, we're not going to spend a lot of time on it because you already know it. It's the same as all the other functions. Let's turn the page. There's a question I always get, and we haven't answered it yet, which is, how does the base affect the graph? And we haven't really talked about it even for exponential functions. Let me get my graphing calculator and try to graph this for you. So if I go to graph, there we go. So if I were to graph y equals 2 to the x, 2 to the x. Oops, no, that's not correct. There's y equals 2 to the x. Now, what if I change that base? So y equals 3 to the x. tab, y equals 3 to the x. It becomes steeper. And really, it's the same point it goes through. It's the same asymptote, but the steepness of that exponential curve increases. This makes sense, right? If you're doubling versus tripling, well, obviously tripling is going to be a lot worse. If I do my next graph, I did 4 to the power of x. We would imagine it's even steeper. So without getting into it too much, I have this point 0, 1. So if I have a base, as the base changes to different integers, the steepness of my graph changes. Let's get a cool color here. Oh, how about green? Perfect. Okay, the reason we talk about this now, I guess I'll put a little note here. Increasing the base increases the steepness. The reason I talk about it now is because we can apply the same thinking when looking at logarithms. And I can graph this, but really it's going to be the same thing. You can imagine if I were to reflect these things, the steepness of my log base 2 is not so steep over here. So this is y equals log base 2x. Y equals log base 3x. And if I get my cool color, y equals log base 4x. And this is 0.10. In the same way, increasing the base decreases the steepness. So hopefully that answers that kind of question we've been thinking. Okay, finally we're just going to look a little bit more at this idea of how these two functions interact with each other. Remember FOF, which is function, composite, and inverse function? This was the identity function, if you remember. So, and again, we're going to look at these two ideas from yesterday. If you have log base a of a to the x, these undo each other, and I'm just left with x. Similarly, if I have a raised to a log x base a, well, these undo each other, the exponent and the logarithmic, and I'm left with x. Because if you have a function and its inverse, composite, or subbed into each other, they undo each other. So we're just going to kind of formally name this again because your textbook makes a big deal of it. Log base 10 of 10 to the x, for example, well, that's just going to be x. Or over here, 10 to the log base 10 of x, well, that's just going to be x. It's like a shortcut. What about if a is equal to e? Then we'd have ln e to the x. Well, the ln and the e undo each other, so I'm just left with x. Or if I have e to the ln x, the e and the ln undo each other, I'm just left with x. IB is all about questions like this. They're very quick, right? You can look at this, it's overwhelming, but then you can jump right to that. Let's do a few last questions before we get to our homework. If I have this expression I want you to solve, remember, solve means what x value makes this true. Well, I don't know how to solve hard things like this, but wait a sec. 7 raised to 7 base, well, these just undo each other, and I'm left with x. Be careful, we don't say that they cancel out. They undo each other, right? So I'm left with x. Now this is easy algebra to solve. I bring the x to the other side, so I have -4 is equal to x. Now, the next question is getting to the kind of problem we had a few lessons ago when we looked at the Facebook data. How do I solve for an exponent when I have a logarithmic equation like this? And we're going to learn and spend a lot of time on this. The one hint I'm going to give you now is that you could, whatever you do with an algebraic expression to the left side, you have to do the right side. So if I wanted to turn this into that, well, I would just log base 10 it. So log base 10, 10 to the x. This is a great idea because now these will undo each other and I'll be left with x. But if I do that to one side, I have to do it to the other. So that's I haven't broken any rules. That's a valid rule. The first day you learned algebra, we talked about what you do to one side, you do to the other. And we'll spend a lot more time on the idea of logging both sides. But for now, just watch. Log base 10 of 10, well, that undoes each other, so I'm left with log 12 base 10. You could type that into your calculator now and actually get an answer, right? Log base 10, 12. That gives me approximately 1.08. Similarly here, if I wanted to solve this, to undo the e, I could ln both sides. The ln, which is log base e, and the e cancel out, so I'm left with x is equal to ln 4.15. Type it into my calculator, ln 4.15. That gives me an approximate answer of 1.42. And I ln'd both sides. So today we've looked at the logarithmic function. It's just another function. Now you know the shape. Now you know how it works. You've already started to get familiar with logarithms. Your homework then should not be too overwhelming. It's page 119, number 1 to 5, page 120, number 1, and page 122, number 1 to 9. Good luck, and we'll see you next time.